All right, so we're starting today's discussion on active micropumps. We started talking about it yesterday, but we'll get more into it today. We'll talk about the different types of displacement micropumps and dynamic. So we ended up the last class talking about micropumps, and we said there's two categories of micropumps. The passive micropumps are the ones that require no energy input, and the couple examples we gave on that were the pumps that were based on capillarity. Just the capillary action of liquids. The surface tension force is what pushes the liquids through the channel, rather pulls the liquid through the channel. Okay, there's two types of surface tension driven micropumps. But a lot of the pumps you'll see in the literature are what's called the active micropumps. Active micropumps are where you can deterministically control where you want the fluid to go, when you want it to go, and how much you want it to be pumped. Right? So this is the type of more of an engineered system that's more useful for doing more quantitative control over your chip. So there's two general classes that, according to this review, I mean, I would say that makes sense. And there's one class of pumps that's based on displacement, typically at some type of diaphragm. And there's another category of pumps, which we'll hopefully get to at the end of the class period today, where you're actually adding energy into the fluid itself, either by electric fields or centrifugal motion or acoustic methods or magnetic methods. You're actually creating a body force into the fluid that's moving the fluid. And these displacement pumps are more, I guess, more intuitive in the sense you're pushing the fluid along using a series of membranes, reciprocating diaphragms, for example. So we started talking about diaphragm micropumps really quickly. The key parts of a diaphragm micropump: you have a diaphragm that can expand or contract or deflect in two different directions. And so if the diaphragm deflects in one direction, that increases the chamber volume. That's the expansion or the suction stroke. And when it pushes in the opposite direction, thereby decreasing the chamber volume, that's called the contraction or the discharge stroke. Now, if you just had a diaphragm on its own that was just vibrating back and forth, you just get bidirectional motion of the fluid. The fluid would go into the chamber and out of the chamber. Okay, you wouldn't get any pumping effect. The key part is to have two valves, and these are check valves, which will only allow fluid flow in one direction. These valves rectify the flow, rectify the bidirectional flow that the diaphragm provides, and rectifies it into a single directional flow. Okay, and remember the check valve is just something that only allows fluid flow in one direction. This is the inlet valve. It opens up during the expansion stroke. The outlet valve is closed at that point, and during the contraction, the inlet valve closes and the outlet valve opens. And for a diaphragm pump, the flow rate is basically just the delta V in the chamber, the change in volume as the diaphragm expands or contracts, as the diaphragm moves. It changes the chamber volume, that's the delta V, and then F is the frequency. Okay. Certain technologies like electrostatics will give you very fast frequencies but not much displacement. And other technologies will give you more displacements but not as high frequency. So these diaphragm pumps, because they're so similar to the science, or the basic concept is very similar to larger scale diaphragm pumps. And there was a lot of effort in the late 90s and early 2000s to create micro scale diaphragm pumps. And so that's the reason we're starting off with the diaphragm pump discussion today. So because this is I would say, relatively mature area by this point, you can look at there's a lot of review papers on micropumps. This is just one of the very highly cited reviews by Laser and Santiago. A review of micropumps was published in 2004. There are many other micropump papers focused on specific types of micropumps. But this was just a general overview. And it's nice because it talks about some of the general concepts in diaphragm micropumps. So with the diaphragm micropump, remember you need a chamber, an actuator, a diaphragm, and then the check valves. So these are the different possible actuator designs. Just to give you a breadth, the driver or the actuator could be piezoelectric, electrostatic, thermopneumatic, or it could just have external pneumatic control. And so let's look at a few examples here. So in terms of actuator designs, what we're talking about is how do we actually move the diaphragm. So we have to have something in there that moves the diaphragm. So starting off with one example here, this is a piezoelectric actuator. So this piezoelectric disc, remember I mentioned piezoelectrics are devices, are materials that when you put a voltage across the material, that material actually expands or contracts. Okay. It doesn't actually expand or contract by very much. The actual displacement or the movement of it is relatively small, and you need relatively large voltages. But in microscale devices, the piezoelectrics can be useful since you're talking about a small device to begin with. So you have a diaphragm here, and you put a piezoelectric disc on top of it, and you bond that disc to the surface of the diaphragm. When you apply a voltage, what happens is that the piezoelectric disc, it becomes thicker, but in the radial direction it contracts. Remember, if you expand something in one direction, it's going to shrink in the other direction, right? That's the Poisson's concept. So when you apply a voltage, this thing shrinks in the horizontal direction, expands in the vertical direction, and as it does that, it's applying a tensile stress to the diaphragm. It's applying a compressive stress to the diaphragm, and that will cause the diaphragm to bend downwards. Okay, so you're not pushing it down directly; you're applying a compressive stress, which ultimately pushes the diaphragm down. So that's one way that you can control it. These are a few different designs. So this is the design where you're using the compressive stress. Another design down here is where you have the disc in a chamber and connected to the diaphragm in one direction. And when this disc expands, the expansion of the disc itself is pushing the diaphragm down. Okay, so you can leverage both types of displacements in the piezoelectric disc to do the diaphragm pumping. Now with piezoelectrics, remember, there's not much displacement at all. Very, very little displacements. However, you can make up for that by having a fast frequency. You can actuate those piezoelectrics at thousands to millions of cycles per second. So even if the displacements are small, you can still get some flow in there. Now notice that these are the check valve designs. Okay, these are just some similar to diaphragm check valves. They only allow flow in one direction. All right, another example of an actuator design is what's called thermopneumatic. Let's say you have a working fluid that's initially at a certain temperature and a certain pressure. And then you have a thin film heater in there. Okay, so this region there's a heater. When you apply electric current to that heater, it heats up. When it heats up, it changes the pressure of the working fluid. Right, so you're basically heating up and increasing the pressure. PV equals nRT. Remember the ideal gas law. If you're working with gases, then that's the relevant rule there. But liquids, when you're working with liquids, there are some ways that you can cause liquids to expand too. For example, if you have a heater in water, and we're getting into a different class of pumps, but if you heat up water, for example, enough, if you get past the boiling point, you're going to actually blow a bubble, right? Bubbles will start to come out. That's called a phase change micropump, and that can also be done this way. You just have a heater, you create a bubble here, and that bubble actually pushes the diaphragm out. Okay. Microbubbles, you can actually make them very quickly. They're not as fast as electrostatics or piezoelectrics, but you can make 10 milliseconds, 100 milliseconds. You can create bubbles and expand and collapse them. So thermopneumatic means a temperature is being transduced into a pneumatic pressure, and that's what causes the diaphragm to deflect. So down here is an electrostatic example. So the electrostatic device has two electrodes here. When you put a voltage across the two electrodes, the upper electrode builds up a positive charge, and the bottom electrode builds up a negative charge. This is what a capacitor is, right? You put a voltage across two plates of the capacitor. One One plate has positive charge, one plate has negative charge. And we talked about this type of actuator before. When you place that voltage on there, the positive and negative charge have an attractive force, and that attractive force can cause will cause this diaphragm to deflect and move upwards. So this is another way you can get contraction. So electrostatics are quite fast also. Sometimes you need relatively large voltages. Sometimes tens of volts is possible, but often you need more than 100 volts. So that's something to keep in mind. But electrostatics can be used as pumps. This is a technology, by the way, that doesn't work very well at the large scale. If the electrodes are far apart, then you need if they're 10 times, if the distance between the electrodes is 10 times larger, even millimeters, let's say, or millimeters to centimeters, then the amount of voltage that you need in order to build up a sufficient electrostatic force between the plates is too high. It's actually greater than the dielectric breakdown of air, and you'd end up getting sparks between them instead of an attractive force. The final type of pump, and in fact this is what's used in the quake valve scheme, is to just have an external source which provides that pressure. Like, for example, if you want this diaphragm to be deflected downwards, then you just have gas flow into the chamber that basically bends the diaphragm down. All right, so this high pressure is coming from off the chip. Whereas these other technologies that you saw here, the forces are being generated on the chip. All right. Now, the reason why the quake valves are very commonly used compared to these other technologies is because the quake valve has no expensive parts in it. Once you put a piezoelectric device in there, in your pump, once you put electrodes in your pump or thin film heaters in your pump, it means you have to do a separate fabrication step. Okay. Whereas a chip like this, you can make just out of this PDMS, a plastic or elastomer. Okay. Adding metals and piezoelectrics into the device increases the cost of the device quite rapidly, to the point where it's not disposable anymore. So one of the reasons these designs are popular is because all the expensive stuff is off of your chip. The downside of this design, though, is that you need these external pneumatic controllers, the solenoid valves that sit away from the chip, and you have a gas line that goes into the chip. Okay, so the complexity is taken off of the chip. Whereas with these types of designs, all you need is an electrical input into your system, and the electrical signal will control the valves. Right, so many different types of actuator designs depending on the required application. So now let's talk about two types of valve designs. All right, we'll talk about moving valves first, or dynamic valves, and then we'll talk about static microvalves. Okay, so this is the second part of the second component of the diaphragm micropumps. Or, I'm sorry, the last component here, the check valves. A few different kinds of check valves here. One type is a moving valve. This is the type that was shown in the diagram earlier, where you have a flap that moves out or moves back. A few examples of how these valves were made. It actually can be a little tricky to create valves on a chip, okay? Because this valve actually has to be free to move. A lot of times when we do microfabrication steps, the parts that are in there, if, for example, let's take a look at this on the left side of this diagram here. So this is one of the valves. Okay, if you were to create this pattern in the device using the conventional soft lithography technique, then this valve would actually be fixed to the bottom surface of the channel. It would be attached there. But we need this valve to actually to be able to move in the left and right direction. So just that one little thing, it turns out to make valve fabrication kind of complex in some sense, because the flap needs to move. So in this particular example, they made a valve that rotates parallel to the device, in plane with the device, and the way they freed this valve is by using photopolymerization. So instead of using the same soft lithography process which is used to make the channels and the channel walls, they actually used light to photopolymerize a hydrogel within the channel. So we talked about stop flow lithography, we talked about photopolymerization back in the microfabrication module. So that's what they used to make this valve here. Besides that, the other concepts are what you've seen before. You have a diaphragm, and then you have an inlet valve and an outlet valve. Okay, when this diaphragm goes back and forth, and these valves are going back and forth, you can create a pumping motion. One more thing I want to point out about these valves. Notice what the valve design looks like. It's literally just a flap, but if you flow fluid from left to right, this valve can deflect from left to right. If fluid flow goes in the opposite direction, from right to left, notice that this valve, this little flap, will get pushed up against the wall right next to it. So that will block the fluid flow. It only allows flow from left to right. So this is one type of a flap check valve. It's called a hydrogel check valve. Another type of valve is where the diaphragm itself is sectioned into 3 different components, and the 3 parts of the diaphragm move up and down at different rates. Now this is at different times. This is very similar to a peristaltic pump, which we'll talk about a few slides later. But for the purposes right now, you have this. Let's see how this works. So this is the main diaphragm. Think about this as the main diaphragm. When this is expanding, it deflects upwards, and at the same time, you deflect this one upwards to allow fluid flow into the main chamber. This one is closed at this time. Okay. During the compression stroke, the diaphragm moves down. This one is closed, and the last one is open. So whatever volume was in the liquid volume was in the chamber, it gets pumped out through the right side. So that's a dynamic diaphragm valve. And then a slightly different twist on this design is a throttle design here, which basically modulates the hydraulic resistances on the input and output channel. So this picture here is actually doing the same thing as these other designs. So let's just look at how this works here. The throttles are in, there's 2 throttles, and the throttles is basically these 2 little posts here. There's a diaphragm, and then on top of that there's a piezoelectric disc. And that piezoelectric disc can cause the diaphragm to bend upwards, and in fact it causes the entire substrate to bend or deflect like this. These deflections are greatly exaggerated, but you kind of get the idea here. So when the PZT contracts, it's going to cause the diaphragm to bend upwards, that will open up this portion of the chamber volume and close this portion of the chamber volume. And when it deflects in the opposite direction, the opposite thing will happen. You'll get this will block this post here and leave this post open. Right, so these posts are acting as a valve. Okay. Now a key concept in here is that the piezoelectric actuator is offset. It's not in the center of the membrane, it's really off to the side. That's what creates this asymmetric motion. This asymmetric motion opens up the region below this throttle during the inlet stroke, and then it closes this region off during the outlet stroke and opens the outlet region. Okay, so this type of pump design is sort of a segue into the next set of pump designs, the diaphragm, the static microvalves. Now you'll notice what these things had in common is that these valves were all moving. these valves were actually physically moving parts. Now, whenever you have physically moving parts in a device, you're always concerned about the wear of the moving parts, like whether those things will get damaged or break, and so on. Anything with moving parts is inherently less reliable. Now, one of the reasons, computer chips can operate for years without any problems is because they have no moving parts in them. So, one way to remove moving valves. So the valves are probably the area of the component in the pump that's most likely to fail. You can replace those moving valves with what are called static microvalves. All right, static valves are they have a fixed geometry. They require no moving parts and no additional energy input. So that makes them very simple and robust alternative to the moving valve designs that we saw in the previous slide. So how do these things work? In order to get flow rectification, so in order to get this bidirectional movement of the diaphragm and convert it into unidirectional flow, all these designs use one basic principle. The flow resistance in the forward direction is lower than in the reverse direction. So a few different examples here. Let's just look at these in order. This is what's called a thermally controlled viscosity valve. It has two openings here. The geometry of the opening is the same. However, they're at different temperatures. Okay. Viscosity decreases with temperature, so the hydraulic resistance at the inlet and outlet can be modulated. What happens to flow resistance if we decrease viscosity? So if you were to decrease the viscosity of the liquid, is it easier to move fluid through the channel, or is it harder? It's easier. Right. In fact, there's a linear dependence on the hydraulic resistance and the viscosity, if you look back to the equations we talked about earlier. It's a linear dependence. So flow resistance increases with viscosity. Now, if we were to heat, if the outlet is heated and the inlet is not heated, what will happen is that there will be less flow resistance here and a higher flow resistance here. So when the diaphragm pushes down, okay, during the contraction part of it, the fluid flow will preferentially go to the right because there's less fluidic resistance on this side versus this side. Okay, so that's going to be the contraction part of the stroke. The expansion part of the stroke, the diaphragm will go down, expanding the volume. In that case, the inlet choke will have a higher temperature. This will have less fluidic resistance. So the flow rate coming in here is going to be greater than the flow rate coming in here. Right? So as a result, you'll get a net motion of fluid. This is another elegant sort of approach where you have what's called a diffuser. A diffuser is something that has different flow resistances in the two directions, and it's just by virtue of the shape of the channel. So this inlet here, now this design B and design C are similar. Let's look at this diagram because it's I think it's more clear. The diffuser action has less resistance than the nozzle action. So this is the inlet. Don't get confused. I mean, I don't know why the inlet's on the right side of this diagram, but this is the inlet and this is the outlet. So when fluid is going from a constricted area to a wider area, there's less hydraulic resistance here. when fluid is going from when it's going through a small nozzle here and is going through a I'm sorry. When the fluid is going from a large region to a constriction, the flow resistance is higher. Okay. Now this type of thing is well known. It's been studied analytically. It's also been studied experimentally. So again, let me just repeat that since I was a little unclear at the beginning. When fluid is going from as fluid is going through a channel, if that channel is expanding, if it's getting wider, then there's less flow resistance than if the channel is contracting into a small point. Notice that these two channels are actually the same dimensions. The only difference is the large end. You know, these two ends are mirror images of each other. But the inlet, the large end, is connected to the chamber, and for the outlet, the constricted end is connected to the chamber. So these two triangular shaped channels present different resistances whether you're going in one direction versus the other. So the beauty of this type of design is that all you need is two channels that are these triangular type channels, and of course you need your diaphragm. But you don't need to have moving parts. You just rely on the fact that these components have different resistances in one direction versus the other. Any questions on that? This design is also used here too. Okay, this is the diffuser nozzle design.
So you would have to have them in series depending on how much pressure you have in front of you. So that pressure, back pressure might.
Yeah, good point. Yeah. So Jeremy brings up a very good point, and this is a point that relates to all microvalves. There's a certain amount of pressure that each type of these pump and valve designs can generate. Okay. One of the nice things about the check valves that I showed you earlier is that they completely seal. Right? These things don't completely seal; they partially seal. Well, they actually don't seal at all. Like they just offer different flow resistances in different directions, so you can still get a pumping motion. But these are not true valves. They're not true one-way valves. There's just different flow resistances in one direction versus the other. So Jeremy brings up the point about back pressure. You know, like, is a pump like this going to be able to, lift up a tower? No, because the tower, if you're trying to lift something up or you're trying to push some liquids out of the channel. Let's focus on a simple example, right? You're trying to push some liquid through a long channel with a large amount of hydraulic resistance, right? Certain pumps are not going to be able to handle that. Okay, so one of the specifications of the pump is how much pressure can it generate, how much back pressure can it handle. Okay? If it can't generate enough pressure to push liquid through whatever it's supposed to go through, then you'll end up getting like reverse flow. Okay? That is referred to as back pressure. So these types of valve designs, one of the downsides is that they don't offer as much pressure. They're not high pressure pumps. So let's talk. The Tesla valve is another type of design that has different flow resistances in one direction versus the other. So in the Tesla valve, the inertia of the fluid causes it to flow straight at a bifurcation, resulting in different flow paths in the forward and reverse direction. So let's look at this. This is an interesting design here. So let's say fluid is going, the inlet is, it's coming here on the left, and then the outlet is here. Now, when the flow is going from left to right, fluid prefers to go it prefers to keep on going in the same direction. The fluid inertia wants to keep the fluid going in the same direction. Now keep in mind, this is an inertial effect. So this is going to be significant only at higher Reynolds number, when inertial effects are significant. nonetheless, it's useful to look at this type of thing. So when there's inertia present, let's say fluid is coming in at the inlet. The momentum of that fluid is going to want to keep it going down straight this way. When it gets to this bifurcation, the inertia of the fluid will, most of the fluid will end up going this way because it's a short turn. Less of the fluid will go this way because it's more like a U-turn, right? Because there's more of a momentum change that the fluid has to undergo. So when you're in the inlet, the flow is going this way and then straight down this way. Relatively short flow path. When you go in the reverse direction, now the fluid flow is coming in from here. The momentum is going to drive it into the longer channel rather than the shorter one here. All right, since the fluid is going through a longer channel, and then again here it chooses the longer channel, that means there's going to be a larger flow resistance going in the reverse direction than in the forward direction. This is an interesting type of device here. This chart talks about the scaling of diaphragm pumps. So diaphragm pumps are often operated at their resonant frequency to improve their performance. Every mechanical system has, well, never want to say every, but virtually all mechanical systems have some type of resonant frequency. You guys have seen like a tuning fork. You hit a tuning fork, it resonates at a specific frequency. The Tacoma Bridge. I don't know if any of you remember that. Maybe some of the international students, you may not know about it. There's a bridge on the west side of the United States in a city called Tacoma. It's a little bit, just an hour south of Seattle. And so they built a bridge there over a river. And the bridge designers didn't really account for the fact that the bridge could undergo resonance. It can vibrate at its resonant frequency. So when the bridge was vibrating at the wind, there's a big windstorm one day, and that caused the bridge to start to vibrate at its resonant frequency. And you could literally see the bridge, like waves going through the bridge. You could see a YouTube video of this, right? I don't want to like stop class and look at that right now, but you can look at it in your own time. And these gigantic waves, like the bridge, which was made of concrete and steel, was literally just undulating like this, and eventually the bridge collapsed. So when things are vibrating at the resonant frequency, the energy in the system can multiply. The resonant frequency is the most efficient frequency to be operating a mechanical system. Piezoelectric transducers are often operated at the resonant frequency because that's when you get the most displacement out of them. So these diaphragm systems, if you want to get the most displacement and the most efficient energy conversion, you can operate these diaphragms at their resonant frequency. So this graph just shows that, from a design perspective, the resonant frequency FR, it changes with the size of the diaphragm. So if suppose the diaphragm has a radius d, or the diameter, sorry, and a thickness t. Right, the resonant frequency scales as 1 over the diameter squared. Right, so as you go to smaller diaphragms, the resonant frequency increases pretty rapidly. Right, so this is showing the diaphragm diameter in millimeters, and this dotted line here is showing the resonant frequency. So when we scale diaphragms, if we try to make the diaphragm smaller, two things happen. Number one, the resonant frequency goes up. We have to drive it at a higher frequency. And secondly, there's less displacement. Right? Smaller diaphragms will have less displacement. So that's something we also have to consider. So these charts show some of the pressures that can be generated by diaphragms I'm sorry, this is showing, these lines are showing the center line displacement of the diaphragm at different pressures. So you can see that at higher pressures, obviously, we get larger displacements than at smaller pressures, but as we scale down the diaphragm diameter, as I was saying, The smaller the diameter of the diaphragm, the less displacement we get. So that's decreasing the stroke volume. So smaller diaphragms will have less stroke volume, but they'll be operating at a higher frequency. Secondly, to get to Jeremy's question about back pressure, the maximum pressure generated by diaphragm pumps depends on its compression ratio and its compressibility of the medium. Okay, so this is the compressibility of the medium, like this is the liquid that you're working with. You know, the gases have a certain compressibility associated with it. Liquids are incompressible. And EC is the compression ratio of the diaphragm pump. Okay, this depends on the pump design. So this is the delta V divided by V0. So the way to define it is simply like delta V over V0 is just the percentage change in the volume in the contracted state versus the expanded state. All right, if bubbles are present in the pump, it can degrade the pressure generation because there's a Laplace pressure that shows up if the bubble is present. So let's look at an example of a very successful pump. Probably the most commercially successful. And this was before the term microfluidics had even come about. All right, this is the Inkjet printhead. This is the type of device that's used in your bubble jet printers at home, and also the piezoelectric printers. Laser printers use a different technology. But the bubble jet and the piezoelectric jet printers use they essentially were the first example of a microfluidic device that was successfully commercialized. And this was patented back in the 70s, and it was used heavily in the 80s, 90s, and even today. So, one could argue that this is probably the most successful microfluidic device. So the piezoelectric or the inkjet printhead is really just another variation of the RDM, the reciprocating displacement micropump, meaning diaphragm, and then you have something that rectifies the flow. Right, so in this case, the driver is the piezo. Let's look at how this device works here. You have an actuator plate, a piezoelectric disc, an ink reservoir, and the ink reservoir sort of goes into this chamber here, which is conical. And then there's a small capillary leading to the edge of your printhead. Now your printhead, by the way, just like it ejects dots of ink, and the volume of those drops is like picoliters. So this is how an inkjet printhead works. So where was I? Okay. So same thing as before, when the piezoelectric device is activated, when the voltage is activated, the piezoelectric device, it expands in this direction, and that pushes the diaphragm into the contraction stroke. So the contraction stroke is pushing the liquid out of the chamber. So this is the expansion. The contraction here, when this thing returns to its original state, this liquid is retracted back this way, but in addition to that, some of the ink is also pulled in from the reservoir. So the interesting thing about this is that the capillary force at the orifice serves as a check valve. Now think about this capillary force is generating a pressure going from left to right. Right, we talked about surface tension and the fact that capillarity will pull this liquid in the whenever you see a concave direction like this, you can see that the water likes to be at the edges, right? It likes the material that it's in because the water is building up at the edges of it. So the water molecules are going to tug on the other water molecules here, and that generates a capillary pressure going from left to right. It's going to try to pull the liquid from left to right. So that the capillarity acts as a valve. So when this thing goes back to its contracted state, the ink reservoir, the ink gets pulled in from the reservoir rather than getting pulled in from here and back. So there is a rectification that's happening in the inkjet printhead also. Right? Notice that there's no valving. There's no valving on the ink reservoir. No valves here, but there is a capillary valve here. Let's get into peristaltic micropumps now. This is the most common type of a micropump that's used in microfluidic devices. I should say this one and the electroosmotic pumps. So the peristaltic micropump is the most common type of pump. It uses 3 valves to initiate flow. We've already seen an example of this, this famous paper by Stephen Quake's group, Monolithic Microfabricated Valves and Pumps by Multi-Layer Soft Lithography. This was published in Science in 2000. They basically showed that these control lines, there's a membrane connecting the control lines to the fluid lines, and these membranes deflect, as is shown here. So, as the 3 membranes are deflected, you can cause a pumping motion. So I'll get back to that in a second. So the valves are actuated in a sequence by an internal or an external actuator. Okay, and that actuator could be pneumatic, thermopneumatic, or electrostatic. We've already seen examples of how you can displace the diaphragm and cause it to deflect in a certain direction. And we've already seen this one too. The ideal flow rate is just the stroke volume multiplied by the frequency of pumping. Right, so these are a few examples of peristaltic micropumps. This is one that's pneumatic. It's based on the Quake valves. This is one that's thermopneumatic. It's based on the Quake valves. So let's look at this one first. So thermopneumatic, again, I mentioned thermo means heat, pneumatic means gas. So the thermopneumatic pumps heat up a fluid, and it causes that fluid to expand, and the expansion of that fluid ultimately causes the deflection of the diaphragm. So there's 3 different chambers here: heater 1, heater 2, heater 3. And this small, it's hard to see, but this thin region going across here, that dark region, that's the actual channel. Okay, this is the inlet. This is the outlet, and this thin region in the middle here is actually the channel. The white portions here are the membrane. It's the membrane. So when this heater heats up, heater 1 and heater 2 are heated together at the same time. You notice that both of them are deflected. And then after that, the next 2 valves, heater 2 and 3, are activated. Now what this does is that, then in phase 3, only the first valve and the third valve are activated. So the 3 valves operating in succession ensure that you get flow in one direction. It prevents backflow. Okay, there's several ways to think about this. Let's just jump forward to the next slide here, because I think that explains it better. There's a few different ways that you can control each one of these valves in succession to get a pumping effect. This is one way to do it. So let's say you have your 3 diaphragms, and this is the channel where the fluid is being pumped through. Okay, this diaphragm gets pushed down, and as it does, it pushes fluid this way. Now keep in mind, this is also going to push a little bit of fluid backwards. Because if you displace the diaphragm, you're going to get flow this way, and you're also going to get flow the other way. Okay, so a single diaphragm just going back and forth is not going to be able to generate flow, unidirectional flow, like we talked about earlier. But a peristaltic motion is where you have this sequence. So let's say the first one goes down, and then the second one goes down. Now when the second diaphragm displaces down like this, the first diaphragm is preventing any backflow. Right? So the first diaphragm is really serving as a check valve. So when the second diaphragm bends down like this, it pushes the fluid in the forward direction. All right, and then when the third diaphragm bends down, again, whatever stroke, whatever volume is in this chamber, it gets pushed out this way. So at this point, we've pumped a small packet of fluid from left to right. So at this point, you can deactuate all three of the diaphragms together, okay, and you can repeat the sequence again. This is not the only way to control a peristaltic pump, but it's one way. Now, a peristaltic pump, one nice thing about it is that it's bidirectional. If you were to reverse the sequence, if you were to, start with this side, the right side instead of the left side, then you'll get pumping in the opposite direction. So that's a nice little benefit of peristaltic pumps or active micropumps. So again, the way that you can control these pumps, you can use piezoelectric, pneumatic, thermopneumatic, even electrostatic actuators. These types of pumps, the peristaltic pumps, can actually offer a reasonably good back pressure, but the flow rate decreases linearly with back pressure. All right, typical flow rate would be 7.5 microliters per minute at 250 kilohertz. This is if you're using a piezoelectric type actuator. With pneumatics, there's no way you're going to get 250 kilohertz. It'll be more like, at most, maybe 100 to 200 hertz. This is another actuation sequence. This is another type of pump which uses normally closed valves. This is where the channel looks something like this, and the valves are normally closed. The first part of the actuation sequence, you open up the first one to allow fluid to come in here. Then you open up the second one. Then you close the first one. Remember, when you close the first one, you're going to get a little bit of backflow there. And then you open up the third one. You get an inflow of a little bit of backflow of fluid in here. And then you close the middle one, close this one. So ultimately what happens after that actuation sequence, that you have pushed a small packet of fluid forward in the forward direction. Okay, you can look through this on your own. It's relatively intuitive. It just go through the steps on your own one by one. You'll see how it creates this pumping effect. Going back to this earlier slide, you can see here that just a thermopneumatic technique is used. The heaters are controlled in sequence to create the peristaltic pumping effect. This is an example from Albert Folk's book, where they use doormat valves instead of the standard diaphragm valves that Stephen Quake used. Doormat valves give a little bit better sealing, but again, they're a little bit more tricky to fabricate. So questions on peristaltic pumps? Pretty straightforward concept, right?
That's a dumb question.
Yeah.
When you increase the back pressure, why does the flow rate decrease?
Good question. So with peristaltic pumps, like Jeremy was asking, why does the back pressure decrease? Or with higher back pressures, why does the flow rate decrease? So that has to do with, if you go back to this diagram here. Okay, this diagram actually doesn't do a great job of showing it. Let's do this one. Okay. You notice that in these pumping steps, in some of these pumping steps, you're getting a little bit of this backflow. Right? You get a little bit of backflow here. Notice that in this step, you get a little bit of backflow here. Right? A little bit of backflow happens with peristaltic pumps because whenever you move a diaphragm, it's basically a bidirectional. It's a bidirectional pumping motion. The only part of the peristalsis where you don't get that effect is if one of them is closed, right? For example, when we close this diaphragm here, the fluid can't go back this way because this one's closed, right? And so the fluid ends up moving forward. in this particular step. But remember, in the first step, when we put the first diaphragm down, there's flow in this direction, there's also flow in the opposite direction. Okay? So it turns out the more back pressure you have in the system, if there's a thing that's pushing back on it, there's going to be more backflow in each of these steps. And that's why you can't generate as much of a flow rate. Now there's a nice concept that you can cascade multiple peristaltic pumps together in series with one another, in which case you can get a certain flow rate while being able to handle a larger back pressure. So because micropumps are small, it's easy to cascade multiple ones together. So, and in fact, that type of approach has been used. One of my colleagues, from Michigan, when I was in grad school, he was working on an 18-stage micropump. So it's basically a diaphragm pump with a check valve at the inlet and the outlet. It was a gas pump, but he was using the gas pump for gas chromatography applications. His name is Professor Hansep Kim. He's at the University of Utah now. He was at Michigan before. And the work was done under Professor Khalil Najafi's group at Michigan. So for their particular application, they had to have a pump that provided reasonably high back pressures because the gas had to go through a very long channel. It also had to provide a sufficient flow rate necessary for gas chromatography. So in order to make a pump that met these specifications, they actually had to cascade 18 stages of peristaltic pumps together in order to get it to work. It was a very, very challenging device to make, but it had a very good performance. At the time it came out, I believe it was the highest performing micropump the highest performance gas micropump in the world at the time. I'm not sure how things have changed now. That was back in 2007. Okay, so any other questions on peristaltic? All right. There's some technologies. I will say that this rotary pump technology is kind of interesting, but I haven't seen it. I haven't seen that many recent papers on it. Nonetheless, it's the reason why I think this technology is kind of interesting is because you can attach, you can think about attaching external rotary motors, like these tiny DC motors that you can get that are used in toys. They create a rotary motion, right? So the concept behind rotary micropumps is, could you use a rotary motion of a small spinning item? Because these types of DC motors are really inexpensive and they're very compact, right? Is there a way that we could use those types of motors and use it to create pumping in a microchannel? So basically to make portable devices. So these rotary micropumps sort of take advantage of, or they try to exploit that concept. So you would have this DC motor, and the spindle on the DC motor would somehow be connected into your microfluidic channel, and thereby creating a pumping motion. So a few different ways that you can do this. So if you want to make a rotating micropump, you can, let me do a correction here. These are the types of, these should be the types of rotary micropumps, not the parts. There, that's better. Yeah, so this type of design, the rotating shaft type design, is where you actually have a freestanding structure within the microchannel, and the spindle of your motor is connected into this chamber. As this rotary motion happens, you can imagine that a fluid packet goes into this region, it gets transported over to this side through the rotary motion. That's one way you can pump fluids from one thing to another. What a nice thing about this type of design is that the flow rate can be very easily controlled just by the rotation rate of the motor, and that's very well controlled. Okay, so turbine pumps work sort of in this idea. Now this is something that is done at the macro scale, right? This is not really taking advantage of the physics at the micro scale. It's really just a basic, it's just a straight up miniaturization of it. There's no scaling advantage really. The second one, this is called, it's referred to as an eccentric viscous type of micropump. This requires you, this only works in a microscale system. So you have basically a rotating cylinder here like this, and it generates non-uniform shear stress. Okay, so this rotary motion here is going to generate, it's going to cause a fluid to move from left to right on the top, and it's going to force fluid to move from right to left on the bottom. If you were to take a cylinder in a pool and just rotate it around, it's going to create a rotating motion of the fluid around it, right? So that on its own is not that useful. It's just a rotary motion. However, if you displace that cylinder to the side of the microchannel, what will happen is that because you're very close to the walls here, there's a lot of hydraulic resistance in this region and a lot of shear stress. So you'll have less fluid motion here on this side versus the top side. As a result, you'll generate a net flow of fluid in from left to right. Okay, this is a rotating motion. I'll mention it again. This is the shaft is rotating in a circular motion, and if this was sitting in just an open space, it would just rotate the fluid. But now we have it inside a microchannel, and it's close to the wall. So this is going to create a rotary motion of the fluid. However, it's going to become non-uniform because on this side there's a lot of hydraulic resistance because this little region here, this channel that's formed here is so small. The dimension of this channel is small. The dimension of this channel is much larger. So there's more flow resistance, which causes there's more flow resistance for fluid to go back this way, less flow resistance for fluid to go forward on the top here. So that will ultimately create that'll create a pumping motion. Yes.
For the first design, how to prevent the liquids remains in the circle, but other than come out of the channel?
Oh, how do you prevent the liquid from just staying in the in these regions here? Yeah, that's a good question. By tilting the blades appropriately, you can get the liquid to preferentially go in and then come out on the other end by angling the blades in a certain direction. Okay, so another way you could do this is by creating a rotary micropump is by rotating the cover plate. If you have a spiral channel, and let's say the draw this one out. Oops. So if we're in a laminar flow type environment, there we go. If we're in a laminar flow type environment where at the bottom this is the bottom of the channel, and this is the top. Now if we were to take this part of the channel and move it, then if you move the wall, the fluid has to go with it, right? This was the example of couette flow. That if you go back to the microfluidic module, if you were to move one of the walls while keeping the other wall static, you can drag the fluid along. Again, there's a linear profile that develops here, and that is called couette. Flow. Okay, you can go back and check the notes on that. So what's happening in in here where you have the spiral channel If you have a spiral channel and you're moving the walls, that Couette flow is dragging fluid along. That rotating motion is causing fluid to be dragged through the length of the channel in a corkscrew type fashion. So that's one way you can do this. And then finally, this other example here is a static microchannel with like a rotating disc. So as this disc rotates, it pulls in a little bit of fluid on the left in the inlet and pushes it out on the outside. So all examples of where rotary motion is being converted into flow in the channel. All right, next group is the phase change micropumps. There's a few different examples of this. We'll just look at each one at a time. I mentioned this earlier, but basically phase change micropumps is where you're changing you're creating bubbles, or you're changing you're changing from one phase to another, and as the medium changes from one phase to another, you can create a pumping effect. The most straightforward example here is just generating bubbles. So the formation of a bubble can displace the fluid. One way is to do a pneumatic technique like this. This is an example of a pneumatic bubble pump. So thermal expansion and translation of a bubble using a temperature gradient. So you have 3 heaters here, and this is your channel up here. You heat up you activate this heater so that the temperature increases beyond the boiling point of the liquid. So you generate a bubble. A pulse of electrical current to here will generate a certain size bubble. Okay, and then these 2 heaters are being used to generate a temperature gradient, because this bubble will actually move in response to the temperature gradient. The reason why the bubble moves, I'm not going to get into right now. It actually has to do with the Marangoni flow, surface tension driven flow. Bubbles and droplets, they actually move from high to low surface tension. So if you create a temperature gradient, a bubble can actually start to move. So that's why the bubble that's generated here moves from left to right. Okay, so as the bubble is generated, though, you can see that fluid is displaced from left to right here. So this particular example was generating a bubble and then moving that bubble. So another way you can think about is expanding and collapsing a bubble. Right? Create a bubble and then let that bubble collapse. Okay? If you do that repeatedly, right, you're expanding and then you're contracting, expanding and contracting. That's a bidirectional motion. Right? It's pushing out the fluid on the expansion part of it, and when the bubble collapses, it's pulling the fluid in. Similar to a diaphragm pump, right? It's a bidirectional motion. So in order to rectify that into flow, you have to have check valves. So in this case, they are using the diffuser nozzles to get the effect of a check valve, to rectify the bidirectional motion of an expanding and collapsing bubble, and rectifying that motion into one directional motion, fluid flow from the left to right. So how do they generate that bubble and collapse it? They just have a small heater in this chamber here. So this design, the inlet is here, the outlet is here. This part that you see going through the middle is the channel. The black regions here are basically an electrical connection. These are metal lines. And in the middle of this chamber here, you can see that we have 2 metal lines here that are just for the purposes of heating. A wide electrical line doesn't have that much resistance, so electricity flows through there easily. If you have a really narrow line, the electrical resistance of that region is large, so there will be more joule heating in these thin regions. From the purely physics standpoint, if you have electrons flowing from this top pad to the bottom pad, this constriction here, you're forcing all those electrons to go through a very narrow region, right? That actually generates heat. So this is called a joule heater. When you apply a voltage between here, you generate heat, you generate temperature, and if the temperature is sufficient, then you'll generate a bubble. So you're generating the bubble by activating the temperature, and when you remove the temperature, it'll cool down, the bubble will collapse. The diffuser elements, this element here and this element here, rectifies that the bidirectional motion of the expanding and collapsing bubble and rectifies that into flow. This example here on the right is called an electrochemical pump. So electrochemical bubble micropump, it uses the electrolysis of water to oxygen and hydrogen to form bubbles. So the let me just pull up. All right, just to show you how easy this is to find, electrolysis of water. Some of you have probably seen this before. So maybe something you've done in your chemistry classes. You have two metals, right? And in those two metals, you put those two metals are in water, and you put a voltage across the two electrodes, right? The reduction reaction takes place. The electrons from the cathode is given to hydrogen cations to form a hydrogen gas. So this is what happens at the cathode. Two hydrogen ions, which are in the water, plus two electrons form hydrogen gas. So H+, remember, water, for those of you who are chemists, this will be a relatively easy concept. But remember that water is always in equilibrium with H and OH. Let's see here. Let's just draw this setup here. So we would place a voltage between these two electrodes here like this. And this is in water. Now, water, H2O, it is in equilibrium with H plus and OH. So there's H2O molecules in water, there's also hydrogen ions, there's also hydroxyl ions. So a more acidic solution will have more hydrogen ions, a more alkaline solution will have more OH ions. But what happens in this reaction is that the hydrogen ions react at one of the electrodes to form hydrogen gas, and that will ultimately form bubbles of gas at one of the electrodes. Okay. So the reduction reaction happens at the cathode. Two hydrogen ions, which is dissolved in the liquid, combines with two electrons. The electron is coming from the fact that you put a voltage on there, reacts to form hydrogen gas, H2. And this is in gas form, so it can form at a sufficient concentration, it will actually form a bubble. Oops. So we can leverage this, we can take advantage of this, because whenever we can form a bubble, we can get a pumping effect. So the way that the electrochemical bubble pump works, it uses the electrolysis of water to oxygen and hydrogen, forming bubbles. Now at one electrode you form hydrogen gas, and at the other electrode you form oxygen gas. So I didn't show you the equation for the oxygen, but it's a similar concept. You can look up the electrolysis of water. You apply a voltage between these two electrodes and you generate these bubbles, and the bubbles is displacing whatever fluid is in this chamber, so it pushes the fluid out. The downside to this is that when you generate bubbles in a chamber, it generates Laplace pressures. The bubbles are sometimes hard to get out. And so these types of things are generally useful for single for single-use type things. If you just have some drug inside a chamber and you want to push that drug out of the chamber, so one-time use kind of thing, then electrochemical pumps can be useful in that regard.
But for this one, there's not the cavitation of the bubble. So what's...
Yes, for this one, the bubble is not collapsing. Yeah, that's a good point. In the thermal one, or when you increase the temperature of the water, you're increasing the water to beyond its boiling point, so the water starts to vaporize, and that's what the boiling is what generates the bubble. So obviously the boiling will stop if you decrease the temperature, and if under the right conditions, a bubble will then collapse and disappear. With these types of things, once you've created these bubbles, it's not possible. It's very, very difficult to take the bubble away. You've generated a lot of hydrogen gas or a lot of oxygen gas, enough where the gas cannot be dissolved in the liquid anymore. It forms its own bubble. And once you have that bubble, it's difficult to remove that bubble. So that's a good point. These are kind of like one-way type devices. So in terms of power consumption, thermal devices obviously have a higher power consumption, and because you're using such high temperatures, you have to be a little careful if you're trying to do something in the body, for example, or if you're doing something which requires a biological assay, because the temperatures can obviously kill things around there. That same type of issue also exists with electrochemical. You're not increasing the temperature. However, some types of electrochemistry, if the electrodes can potentially be toxic, so you have to be careful with that. But in general, electrochemical pumps, they don't require high temperatures. They can be done with more inert electrodes, so they're a little bit more biocompatible than the thermal type approaches. Okay, but again, it's once you create these bubbles, it's difficult to remove them. So these are a group of micropumps that rely on a phase change. Yes. Yeah.
About the bubbles. Here, it's go up because of the lower density. Because
So in this case, the bubbles are being generated at the electrodes, but the bubbles displace the fluid around it. So the bubbles themselves are pushing the fluid out. Now, are you asking why the bubbles themselves are exiting? Well, if you have it in a setup like this, where it's vertical like this, the bubbles will rise, and they'll exit the chamber because of the difference in density, like you said. Yes, that's a good point. In microscale devices, density effects tend to play a smaller role. So sometimes the Laplace pressures and the affinity of the droplets to the walls of the channel make it difficult for the bubbles to just go up, to go up vertically. But it'll still work. It'll still work. So if you want, one way to expel the bubbles from the chambers is, you can use the density effects to do that, like you're suggesting. Okay. Good point. So now another approach entirely is to use centrifugal pumps and valves. Let's see how many things we have. Okay, I think we can finish in the next half an hour. Nope. So now we're getting into some of the pumps where we add energy into the system. Let me do this thing real quick so we can finish up the displacement micropumps. Okay, again, just for context, we're talking about a lot of different pump designs, but we're starting off with the displacement micropumps, and then we're going to get into the dynamic ones. So right now we're just going to talk about one more quick one with the displacement micropumps and then get into the dynamic ones. So these ferrofluidic displacement micropumps, it's an interesting way to pump fluids using something called a ferrofluid. A ferrofluid is a magnetic fluid. And some of these ferrofluids are immiscible with water, so they're kind of oily. This is what one type of design might look like. So the ferrofluid is here. You have 2 plugs of oil around it, and then your actual channel looks something like this. Now, this ferrofluid is actually acting as a diaphragm. There's an external magnet, and you move that external magnet back and forth, left to right, or in this case, like up and down. As you move that magnet up and down, the ferrofluid, which is magnetic, will also move up and down. Right. So this up and down motion, you combine that with 2 check valves, and that will basically create a motion, a unidirectional motion of the water from the inlet to the outlet. Sorry, inlet is here, outlet is here. Okay, so similar to the concept of a diaphragm, this is actually you can think about this as a piston. The piston is going back and forth, and it's being controlled by this external magnet. So this is a linear type design. Now, one interesting thing here is that remember that water and oil are immiscible. In a microfluidic channel, if you put oil in part of the microfluidic channel and then you have water here, this oil is literally going to push. It's going to push on the water, but it's not going to mix into the water. Okay, so that's why this oil, in this fluid here, a fluid can act as like a plunger, really. It can act as a rubber plunger. Because in small microchannels, this wouldn't work at a larger scale, right? But in small microchannels, surface tension effects in the immiscibility of the water and the oil are such that this oil won't get dispersed into the water here. It'll literally, this plug will stay together. That's what allows you to use this as sort of a mechanical pump, mechanical piston, basically. So this linear design can be made into a rotary design. Oops. So in a rotary design, you might have 2 ferrofluids like this. As you can look through this diagram yourself. As the ferrofluid is being rotated around the chamber like this, that will cause, similar to the rotary pump, where you pull the rotating motion here is going to pull some liquid into this chamber and push a liquid outside of the chamber just due to this rotary motion. So it's similar in concept to a rotary pump. Okay, in this diagram, these M's are the locations of the magnet. The black regions are the ferrofluid, and the gray regions are the sample fluid, the thing that you want to pump. So these are pretty simple designs, but it does require a ferrofluid. Ferrofluids, they are available, but integrating it into a microfluidic chip can be a little tricky sometimes. All right, so now we're going to get into the displacement, or not the displacement, the dynamic type pumps. Okay, this is where we're actually adding energy into the fluid itself, somehow. Okay, and the first type of approach for doing this is a centrifugal approach. Now, I just want to back up for a second here. Let's go back to the slide on microfluidics. Just so we have you can see where this is coming from. If we look at the Navier-Stokes equations, okay, there is these conservation of momentum terms in the equation. Okay, this one has to do with pressure forces. This one has to do with viscous forces. Remember, when we talked about how the Navier-Stokes equation simplifies, into something that looks into a simple equation like this at low Reynolds number. Now, I also mentioned that there's these extra terms here. You know, one is a force that's due to gravity. There's another force that's due to surface tension. There can be other forces tacked on to the end of this equation too. This gravitational force, for example, like if you know, this can play a role too. If the fluid is being accelerated in a certain direction, and that acceleration is very significant, then this gravity force can no longer be ignored. All right, you have to include that, and this provides you a way to actually introduce energy into the fluid itself. So remember, like the Navier-Stokes equations, is you can imagine like packets of fluid moving through a channel. If you could add energy into one of those packets of fluid somehow, then you can get the fluids to move. So we're going to talk, the dynamic micropumps are basically based on that principle. You add some type of additional force in addition to just what the Navier-Stokes equations are talking about. So in this case of a centrifugal micropump, we actually have a centrifugal force that's added into the Navier-Stokes equations. Now, we just think about it intuitively. If you were to sit on a merry-go-round, right, and the merry-go-round spins very rapidly, there's going to be centrifugal force that pushes you towards the outside, right? You know, we're basically made up of water, right? So the same type of thing would happen in a microfluidic chip. If you were to have a disc like this, if your microfluidic chip, let's say, was a disc, and you put your samples in the middle of the disc, somewhere in the middle you inserted that, and then you spin the disc, then what's going to happen, the centrifugal forces are going to push the liquids from the inside of the circle to the outside of the circle. Basically based on this centrifugal force. Now, this particular technology, even though I only have one slide on it in this chapter, oops, I want to point out that this is actually a very popular technology, and in fact, a lot of the commercial devices available right now, this technology has been commercialized by multiple companies because it's very elegant and it's very, very portable. All you need really for in order to pump fluids is a CD player. You know, in fact, some of the centrifugal microfluidic setups have been built by just taking apart CD players or DVD players or Blu-ray players and just using the components from there to do it. It's such a simple device because all it requires is a disc. You know, it requires your microfluidic chip is now going to be like something that looks like a CD, except it has microfluidic channels etched into it. And then you also need something that spins it. Now, that concept is very straightforward, but you can do some very, very nice and beautiful assays with this because you can get some very complex fluid handling. You can also detect, your spinning disk system can also detect biological components. You can separate biological components. For example, these devices have been used in blood separation. These 3 commercial devices that you see here are actually all blood analyzers. They can separate plasma from the red blood cells and so on. But this whole area is referred to as centrifugal microfluidics. Sometimes they're called lab on a CD or lab on a disc because the microfluidic chips themselves are not rectangular anymore. They're usually in a disc type format. So we have the disc, which has more or less passive components on it. You'll put that disc into an analyzer that spins the disc, pumps, which ultimately moves fluids from place to place, and it also has integrated electronics and optical detection systems to look at the results of your chemical assay. We'll talk more about detection in a future module. But let's talk about the pumping effects here. The pumping and valving using centrifugal forces. So in these types of devices, pumping is based on a centrifugal force, and these centrifugal forces are very well understood. It's based on the density of the liquid that you're working with. Remember, the more density you have, the more acceleration you're going to have. So the more centrifugal force you're going to end up having. This is, keep in mind, centrifugal force is based on inertia. Right? So this is one of those things that doesn't necessarily scale very well to the microscale. Right? In microfluidic devices, we always talk about low Reynolds number, which means inertial effects are negligible compared to viscous forces. However, these disks are spinning very, very rapidly. You know, like 3,000 RPM, 1,000 RPM. When the disk is spinning that rapidly, you are generating significant centrifugal forces, significant inertial forces, and that can be then used in microfluidic systems. So the velocity, let's say you were to have a plug of fluid, you know, let's say your disk looks like this, and you have a channel that's going from inside to outside, and you have a plug of liquid in here. Say this is the inlet, and then this is the outlet. And this is the center. You may have your inlet here like this. When you spin the disk, either in the clockwise or counterclockwise direction, it doesn't matter, the centrifugal force is going to cause this plug to move from the inlet to the outlet, getting a pumping effect, just by spinning the disk. Now I should mention that one of the reasons why the centrifugal platforms have become so popular is because they're very similar in principle to something that's typically in a biology lab. It's called a centrifuge. Now, Nick, you're a biochemist. You've seen centrifuges before? Yep. It's basically something that just spins at very high RPM. It's used to, Nick, what is it used for?
I mean, it can be used to, I don't know, isolate a pellet.
Yep.
So it's just, you just kind of put some test tubes in the middle of the machine, and then 3,000 RPM, you get a pellet at the bottom.
Yeah, so the centrifuges, the pellet that Nick is referring to is when you want to say separate, let's say you have cells in a solution, right? And when you apply the centrifugal forces, the cells are actually at a higher density than the liquid around it, so they will actually they'll move faster due to centrifugal forces than the rest of the liquid around it. So they'll actually aggregate towards the end of the test tube. So similar types of things have been done here. But you know, all you need is something that spins. So the infrastructure to do this is very, you know, it's minimal. All right, so the pumping is based on a centrifugal force. The velocity of this plug is equal to this formula here. This is the hydraulic diameter of the channel. This is the density of the medium. This omega squared, is the rotation rate. Okay, notice that this is squared. So when you get up to high rotational rates, you can generate very fast velocities, much large centrifugal forces. These R terms have to do with how far the plug is away from the center of how far it's away from the center of the CD, or the center of rotation, right? You know, if you're on a merry-go-round, you feel more centrifugal forces if you're at the edge of the merry-go-round versus if you're right in the middle, right? So the centrifugal forces are more significant at the outer edge. That's why these two terms appear in the numerator. On the denominator, we have the viscosity and the length. So the length, this is the actual, the length of the plug here, so this dimension here, how long the plug is. And the viscosity appears in the denominator because, you know, the more viscous the liquid is, the more difficult it is, the more hydraulic resistance there is, the more difficult it is to move the liquid through the channel. So U is the velocity here. And the pressure that you're generating, the centrifugal force generates a pressure, and that pressure is proportional to the density, is proportional to the rotation rate squared, and it's proportional to the location of that plug on the disk, the radial coordinate of where that plug is. So that's pumping, okay? So if we go to something, the first generation of centrifugal devices, which was done well before the microfluidics era, just showed that you can move fluids from here to here. Okay, that's interesting, that's good. But in microfluidic devices, we need some more complex control of the fluid. We need to be able to move the fluid from place to place, but we also need to have valving. We need the fluid to be able to stop at a certain places and then continue later. We need to be able to, bring two plugs of fluid together at a certain region, then mix them together. The same things that you do, like if you were in a laboratory and you're pipetting things together. You have to have more complex levels of fluid control. You can't just have fluid going from one end of the channel to the other. There's not much you can really do with that. So the cool engineering that's happened in this whole area of centrifugal microfluidics has to do with the valving. People have come up with cool ways that you can valve the liquids and control its flow. So there's two types of valves, two categories of valves which are popular. One you've already seen. There's something called a capillary burst valve. If you remember, we talked about capillary burst valves earlier. This is what it looks like. So let's say your channel leads into a constriction like this. Okay. Now, if it goes through a constriction and that constriction opens into a larger region, whenever you have a plug of fluid going through here, there's going to, as the fluid is being pushed through this region, before it fills up this larger channel here, there's going to be a moment where there's this curved interface. And this curved interface, by now whenever you have a curved interface, that generates a Laplace pressure. The Laplace pressure is given by 2 sigma divided by r if you're talking about a basic cylindrical capillary, but the relationship is similar for a rectangular capillary. So this Laplace pressure is actually going to prevent the fluid from flowing into this region here. Okay? So this generates a capillary pressure, which is a back pressure. It's pointed from bottom to top. It's pointed this way. So the capillary pressure is given by this equation here. Notice that the interfacial tension is in the numerator, and the dimensions of the channel are in the denominator. This is a similar form to the Laplace pressure equation. The Laplace pressure is 2 sigma by rho if you're talking about 2 sigma by the r if you're talking about a cylindrical. This is the equation for a rectangular. A and B are just some correction factors. So this is called a burst valve for a reason, because this is providing some level of back pressure that's preventing the fluid from going through. However, if the pressure that's being generated by the centrifugal forces, the blue arrow here, if that pressure exceeds the capillary burst pressure of this valve, then that valve is just going to open. And once this liquid here, once it fills up this channel, then there's no interface here anymore. And that valve is basically, it's broken, it's open. So the capillary burst valve, remember we talked about this earlier, it's a one-time use valve. Once the valve opens, it's then open permanently. So they use this technique. The capillary burst valve will, let's say initially you spin the CD at a specific velocity, and that pumps the liquids from the top of the channel. It pumps it through to a region where you have this capillary valve. Now the capillary valve, if you're going at that spin speed, the capillary valve has been designed in a way that the capillary pressure exceeds the centrifugal pressure. So this PC exceeds P omega. At that point, if you want to open the valve, you increase the spin speed so that the centrifugal pressure exceeds the capillary pressure. Then what will happen is that the liquids will break, the capillary valve will burst, and the liquid will continue down into here. Any questions on that? So that's one type of valve. And the hydrophobic valve, works in a similar principle, except it also takes advantage of some surface properties here. You can also put a hydrophobic patch into this into the constricted region. You can also put, you can have an even larger constriction here. Now, each one of these types of designs will have a different capillary pressure. The fact that this is hydrophobic will further prevent the liquid from even entering the constriction. Notice that here the capillary valve is, the liquid goes into the exit region before the pressure builds up. In this case, by putting a hydrophobic patch here, the liquid doesn't even want to go into the constriction region, because if this is water and then you have a hydrophobic region, the water doesn't like the hydrophobic region. So you're going to generate a capillary pressure that resists the flow from going into here. Also, same idea that if the centrifugal pressure exceeds the capillary pressure, that valve will then open. So these are hydrophobic valves. Now, the siphon valves work on a different principle. Now, the reason we need two types of valves is because the capillary valves are designed so that you're going at a slow spin speed and the capillary valve stops the liquid. In order to get the fluid to keep on going, you have to increase the spin speed. But in certain cases, you might actually start off with a high spin speed, and then you decrease the spin speed later during your analysis or assay. So in those types of situations, they use something called a siphon valve. So the siphon valve works in a slightly different manner. It consists of this. This is the main channel region, and then this part here is what they call the siphon. Now, first things first, the siphon valve has to be hydrophilic. So it has to be hydrophilic so that water will, whatever the sample is, will fill into the valve by capillary action. So this fills up into this region here. Now what's going to happen? The way this valve works is that if you are spinning at high speeds, then this liquid here is being exposed to centrifugal forces. So this liquid here is going to push down. The liquid gets centrifugal forces pushes the liquids towards the outside. So the direction of the force is from top to bottom. Centrifugal force here is directed from top to bottom. So the more you spin, the higher the spin speed, you're going to get a centrifugal force that pushes this way, and that's going to push back on the fluid. That's going to prevent the fluid from going through this valve region. When you decrease the spin speed, the capillarity, now you don't have any centrifugal forces, so the capillarity is going to cause the liquid to fill through the rest of this channel over the crest. Once it goes over the crest, once the fluid gets in this region, when you apply a spin speed, it's going to just continue on like this. Okay, so the key difference is that when if the liquid has only filled this portion of the siphon, if it has not gone over the crest, then when a centrifugal force is applied, this is going to actually push back on the liquid and prevent it from going forward, acting as a valve. When you reduce the spin speed, this capillarity is going to bring this liquid around because there's no centrifugal forces to push it back down this way. And the liquid will basically go through your channel. All right, two types of valves. Okay, we're almost out of time here. There's a third type of valve too, which is used in some of the more advanced systems, is that they can use light to open and close certain valve regions. Okay, so there's sacrificial valves as well. Since we're almost out of time here, we probably don't have time to get into the details of how those work. But these are the basic types of valves. Now, I just want to mention again that Centrifugal Microfluidics has been commercialized by several different companies, and you can integrate many functions on there. You can integrate blood separation. You can separate red blood cells from white blood cells, from blood plasma and all that stuff. You can do ELISA, which is an enzyme-linked immunoassay. It's a technique to use to detect proteins. You can have fluorescent detection on board also. Typically, these reader-type devices will have, first it'll have a disc, a region where you can insert the disc and spin the disc. And then it'll also have like a camera. It'll have control elements to control the spin rate. It'll also have various types of optical detectors on there, so that you can, you can imagine if your liquid sample started here, and in an ELISA assay, you actually have to mix your sample with two types of antibodies. One is called an attachment antibody. One is a labeling antibody, and the labeling antibody will generate a fluorescence if you have a certain type of protein. So whatever protein you're looking for, you can design an ELISA assay to cause that protein to light up. So there are optical detectors integrated into these analyzers so that you can see the amount of fluorescence, see the amount of light being given off, and quantify the amount of protein in the device. So some of the detection stuff I mentioned, we'll be talking more about that later in the module, or at a later date. So we're just about out of time here. So next time we are going to wrap up. This was the first example of a dynamic micropump where you're using some type of energy to add, some type of energy is being added to the fluid directly. So next time in class we'll talk about other approaches, acoustic streaming micropumps, and then we'll get into the electrokinetic pumps, which is going to lead us into the next module about chemical separations. So next time in class we're going to start talking about electroosmotic flow, how you can separate proteins using a technique called capillary electrophoresis. All right, so we'll start getting into how electrical fields and devices can be used for doing analytical chemistry. So I think some of you will find that pretty interesting. All right, so let's end there. If you haven't turned in your homeworks yet, leave them up here. And if you have any questions about the homeworks, or I'm sorry, questions about your final projects, let me know.